Electron affinity. This is kind of like the opposite of ionization energy. This is the energy change when you put an electron onto an atom. Okay, so here, neutral atom. Atom gains an electron. There's an energy change involved here. Now, this is often negative, but it may be positive. Okay? Some alkaline earth metals and all of the noble gases have a positive electron affinity. A positive electron affinity means that you have to pay the atom to take the electron. That's not how things usually work, right? If I'm going to pay the atom, it's going to give me an electron. I'm buying it, right? But no, this is, here, you take the atom, you take the electron, and I'm going to give you energy to keep that electron. Why does a noble gas not want an extra electron? Because it's good. It's comfortable. It's happy already. It's got its 8 valence electrons. If you ask it to take another electron, that messes things up. It's like, well, you're going to have to pay me for that. What about the alkaline earth metals? The alkaline earth metals are in group 2A. What's their electron configuration? It's whatever S2, N, S2. So if I put an electron on there, where's it going to go? Into the p orbital, which is higher in energy and less stable. And so that's why alkaline earth metals just really, really don't like an extra electron either. Now, the trends in electron affinities are less regular than the other trends. And so we're going to kind of gloss over some of this stuff. It does decrease, becomes more positive as you go down for group 1A. So as you go from lithium to sodium to potassium to rubidium, it becomes more positive, meaning they are less wanting to have this. Yeah. In the other groups, there's not really a trend at all. We do see that electron affinity generally, very generally, increases, becomes more negative across a period. And this makes sense to me because what kind of an ion does chlorine form? Positive or negative? A negative. And it forms a negative ion by accepting an electron, right? Accepting an electron gets it to the noble gas configuration. So that should be pretty easy. In fact, maybe chlorine will pay me for the electron. It'll be negative. Okay, so it's going to want to do that. But the ones on the left side of the period, like sodium doesn't want to gain an electron. Sodium wants to lose an electron. So as you go across, they become more negative. Except for, the noble gases. And what we observe is the most negative electron affinity in any period is going to be the halogens. Because by gaining one electron, that first electron affinity, they get the same electron configuration as a noble gas. Questions? So here are some actual electron affinities. We do see a trend here that the numbers become more positive, less negative as you go down. There's a general trend going across, but it's very general. It's really almost not worth talking about. Metallic character. This one's easy compared to electron affinity. So these are the properties of metals and nonmetals. And some of these you're just familiar with from everyday life. Malleable means that you can hammer it into a sheet. Ductile means you can draw it into a wire. So metals, you think about a hunk of metal and you hit it really hard with a hammer or something. It doesn't shatter, does it? It dents, right? And if you kept doing that, you could change its shape just by banging on it. Metals will do that. Nonmetals don't. They're brittle. You hit them hard with a hammer and they might shatter or crack in half or something. Metals are shiny. They reflect light. Nonmetals, usually not. Metals conduct heat and electricity. Nonmetals don't. Metals, their oxides are basic, and they are ionic compounds. Nonmetals have acidic oxides, and they're molecular compounds. Metals form cations, nonmetals form anions, metals lose electrons, nonmetals gain electrons. So they're kind of opposites of each other. If you can remember one set of properties, then the other is just the opposite. So metallic character, when we talk about metallic character, we're asking, well, how much is this element like an ideal metal? You know, shiny and ductile and forms cations and all of this stuff. Metallic, not medical. Metallic character decreases from left to right across the period, and it increases down a column. Okay, so we have a periodic table, there we go. So this one is the easiest of all to remember. So we've got that stair-step line, right? It's not on this periodic table, that's dumb. Aluminum, it's just above aluminum. So here's the stair-step line, right? So up here we have these are the nonmetals, and these are the metals over here. So if you can do that, you can do this trend. So in this row here, period 3, sodium, magnesium, aluminum, those are metals, right? And over here, phosphorus, sulfur, chlorine, those are nonmetals. As we go from the left to the right, we go from metals to nonmetals, metallic character decreases. Look at this column here, this family. Nitrogen's a nonmetal. These guys are metals. If you probably have never seen bismuth metal, but these guys down here are metals because they're on the other side of the line. So as you come down, metallic character increases. There's just kind of saying the same thing. So pick one, A, B, C, or D. D. Let's do D. Okay? So we're just going to do this one. So choose the more metallic element, boron or nitrogen. Well, we've got to find them on the periodic table. Yeah, so they're like this. Here's boron, here's nitrogen. Well, which one is closer to the metals side of the periodic table? Boron. So boron is the more metallic. Now, we're not saying it is a metal, we're just saying it's more like a metal. Any questions?